Now that we've learned a little bit of how to differentiate a function, we're going to take a step back, take a slightly wider view, and think about the result of differentiation. The derivative of a function, dy by dx, or f dash of x, tells us quite a lot about the original function. It'll give us information in particular about how that function is changing. So as you move along the x-axis, or perhaps as time goes by, what happens to the value of your function. And if you were to look at a graph like this one of the first things that probably jumps out at you in terms of key features would be the local maximum or minimum points that you go past. As you move along the graph, you find there are peaks and troughs and sometimes little blips, points where the graph is neither going up nor going down. The curve is not increasing or decreasing at these points. It is what we call stationary. And this is inherently connected to the gradient function because any point where the curve is neither increasing nor decreasing is by definition a point where its gradient is zero. So if you're trying to identify these points, which is quite a common pursuit in calculus, you would do that by solving f dash of x equals 0. You differentiate the function, you set the resulting derivative equal to 0, and you solve. You find the roots of the derivative because the roots of the derivative correspond to the coordinates of the stationary points on the original curve. One of the reasons we might want to do this is that the curve may represent the amount of profit that we make for different prices that we choose to charge for our goods. Typically, if you charge too much, you don't sell enough to make a decent profit. And if you charge too little, you don't sell enough because your profit margin per item is too low. Or it might represent the time taken to complete a particular process. There's usually a sweet spot somewhere. And the study of optimization, which we will get onto later in the chapter, is precisely this, working to find that sweet spot where the numbers maybe not too big, not too small, it's just right so that something is optimized. Perhaps the volume of a cardboard box is maximized, or the cost of manufacturing a drinks can is minimized. These problems all come down to finding a stationary point on a curve. The first thing I'd like you to do is, using this diagram, see how many stationary points you can identify. And then the other question to bear in mind as you're looking out for them, how would you distinguish between the different types? What would your natural description of them be? And what is it about what's going on at those points that would help you to decide mathematically which type each one would be? Okay, when you've had a go at that, unpause and we'll see if you've found them all. I think we found 5 altogether. These are the ones that I came up with. I've color-coded mine, helpfully. We've got 3 main types. These ones that I've marked in red are the local minima. So each one of those is a minimum point, but it's a local minimum as opposed to what we might call a global minimum, because the function itself does go lower than these points. All you have to do is choose an x value that's below, let's say, 0.8 or whatever that is, and chances are you'll find a y coordinate that is even lower than those 2 minimum points. But they're local minima because they are, at least within their locality, close to that particular x value, they are the lowest point. Think of it as points where rainwater would gather. If it was raining and this was the relief map of the hills from the side, you can see these are the valleys where the water is going to collect. The local maxima are these ones, and these are also points of equilibrium, if you like. They're points where if you balanced a marble there, they wouldn't move. But unlike the minimum points, where if you balanced a marble there, or even close to there, it's going to end up there. If you balanced a marble on the top of these maximum points, then it's an unstable equilibrium in a sense. So if you just nudged it a little bit one way or the other, it's going to go falling off. And that idea of stable and unstable equilibrium points comes in really useful when we're looking, for instance, at mechanics or doing some more complicated problems involving systems of objects. There is a third type of stationary point in here called a point of inflection. You might call it a blip or a wobble. It's a point where the gradient does get to 0, but it's unhelpfully neither a maximum nor a minimum. If you looked at it just from one side or the other, you might be fooled into thinking it was one or the other. So if you could only see this graph up to x equals 4, you might think you were looking at a maximum, but if you could only see it beyond x equals 4, you might think you were looking at a minimum. Turns out it kind of changes its mind halfway. It looks like it's tailing off, and then it finds its second wind and carries on again. You can get a point of inflection even that isn't a stationary point. Any sort of wobble you get on a graph, try sketching y equals x cubed plus x, or draw the graph y equals tan x, and you'll see some non-stationary points of inflection there. But this particular one is a stationary point of inflection, so it comes under our categories of stationary points. Good thing to look at here is to consider the gradient of the curve shortly before and shortly after each of these points. So see if that gives you any clues about how you would identify each one. And we'll look into that in more detail in a moment. Now you can have a go at a question for yourselves. We're going to make use of the fact that y has a stationary point whenever dy by dx is 0. So you'll need to differentiate this quartic expression to find the gradient function for the curve. Since y is a quartic, dy by dx should be a cubic. And then if you solve, your cubic equals 0. The roots of that equation will correspond to the x-coordinates of the stationary points of the original quartic. So give this a go, see if you can find the x-coordinates of all of the stationary points. Okay, we should have dy by dx equals this, 12x cubed plus 6x squared minus 18x. Remember, the power of each term will reduce, so 3x to the 4 becomes 4 lots of 3x to the 3, and so on. Since the gradient of a constant function is 0, the 4 disappears. The derivative of any constant is 0. And since there was no x term in the original quartic, there's no constant term in the derivative. We just have a cubic that has no constant, which is helpful for us because what we're going to be doing is solving this equals 0. The simplest way to start with this is probably to divide everything by 6. And when you've done that, perhaps you'll be able to pull out a factor of x, and then you're left with just a quadratic which can be factorized, and then we can identify the stationary points. We get 0 from the first factor, minus 1.5 from the next factor, and then x equals 1 from the last one. We should have stationary points at each of these 3 x values. And if you were to sketch the graph, that is what you would find. There's a minimum followed by a maximum followed by a minimum, which also is what you might be predicting given that we're dealing with a positive quartic. So it'll start high and end high. For large positive or large negative values of x, the 3x to the 4 term will be the dominant term. It will dwarf the other terms in terms of size, and therefore whatever the sign of that dominant term is, that's going to indicate the eventual value of the function. The question to be asking yourself here is, for which values of x is this curve increasing, and when is it decreasing? So think about what it means for the curve to be increasing or decreasing. Think about what your intuitive understanding of that would tell you, and see if you can predict for this particular curve when you would say the curve is increasing and when it's decreasing. This next problem is an activity from undergroundmathematics.org. So I've pulled this question verbatim from their website. It's a brilliant resource. I recommend you go and check it out. It shows how the various different topics and ideas and concepts behind mathematics all tie in together, especially at A level, where you start to see links and connections between algebra, geometry, calculus, etc., etc. So we've got 6 different equations and 5 different graphs, which means one of the equations in the list is not represented on the graph. You need to identify which of those, A, B, C, D, or E, is represented by each of those equations. All you know is that there is a maximum point somewhere between x equals 0 and x equals 3. And based on the curves, you should be able to calculate, once you've identified the coordinates of the maximum, you should be able to tell which curve belongs with which one. I'm not going to give you the precise values here. All the working out is on undergroundmathematics.org. You're looking for an activity called floppy hair, I believe, named after the graphs, I suppose. So pause the video, have a go at these, see if you can identify the stationary points, and then come back and you can check if your answers agree with mine. All right, so I got the following: E, C, D, B, and then the last one is A, which makes that 1/6 x, 3 minus x, 5 plus x into the extra graph, and that's shown up on the diagram there. If you want to see the Details of how these are calculated for yourselves, if you've tried them and you're still not getting the same answers as me, or if you want to double check the numbers that you got out the other end more than just visually, then I recommend you go over to Underground Mathematics and see if you can find this activity. Lots more useful things over there as well. The next thing I want to look at is the definition of increasing or decreasing functions. What does it mean for a function to be increasing or decreasing? And the first thing I'd like you to do is to draw yourself a rough sketch of this function. The precise values are not so important here. It's the ideas and how the definitions apply to it that matter. So see if you can indicate on the curve or write down roughly the values of x for which you believe this function is increasing and where you think it is decreasing. And if you can, see if you can link that to what you understand by dy by dx. Okay, so the best way to think about increasing and decreasing functions is to read them from left to right. Perhaps imagine this as a roller coaster and you're going to be moving in the positive x direction. So initially, you're hurtling down a very, very steep section of the roller coaster until you get to the first minimum point, and then you move up, and then you get to a peak, so a local maximum, and then you go down once more to the second trough, and then up once more, and then presumably you continue going up forever. It's that kind of roller coaster. So it looks like these sections correspond to what I would describe as decreasing. Whenever you're moving down, those are the decreasing sections. And therefore, these are the increasing sections. Anywhere where the curve is moving up, as you move to the right, you also move up. And when we refer to dy by dx, think about how the gradient changes as we move along here. Now, these points here are the points where the curve changes from being increasing to being decreasing. Depending on your definitions and how strict you're being, you could think of them as points where the curve is neither increasing nor decreasing, or you might want to have a more inclusive definition and say these are points where the curve is both increasing and decreasing. The official way those words are used in Edexcel, and I believe most of the other exam boards, and in fact university mathematics, an increasing function or an increasing sequence is one which is non-decreasing. That's probably a better way to think about it. So it's something which is either staying the same or going up, as opposed to something that must always be going up. We have strict definitions if you want to describe something which is increasing in the more traditional sense. So it's not staying the same, but it is actually going up by a non-zero amount. You might use the phrase strictly increasing. Now, these are the regions for x for which the function is either decreasing or increasing. So if you were asked in a question to describe the values of x for which the function was increasing, you would give your answer as something like 0.4 is less than or equal to x is less than or equal to 1.8, and x is greater than or equal to 3. So we're including the endpoints, but we're also describing the entire regions for which the gradient of the curve is positive. In other words, the function is going up because the slope is positive, or at the very least non-negative. Here is the gradient function, so we can get a sense of how that connects. Notice that whenever my function is increasing, the gradient function is positive, and when my function is decreasing, the gradient function is negative. And then the awkward bits in between, if I'm at a stationary point, the gradient function is 0, and if the gradient function is 0, I'm at a stationary point. Occasionally those might coincide, as they do here at 3, 0, but that's by no means always the case. If you happen to have a repeated root, then you've got a root, but you also have a stationary point, which means the gradient function will also have a root. But in general, as you can see, the roots of the gradient function do not have to correspond to the roots of the original function. What they do correspond to is the points where the original function is stationary, where it has a stationary point, a maximum or a minimum, for instance. Now, this animation shows you the gradient as it changes, so you can think about the slope of the curve as you move along it. And it's a good thing to have in mind when you're looking at a graph to try to visualize the tangent line so you get a sense of whether you're moving up or moving down as you go along, and how that corresponds to a positive or a negative gradient. Whenever the slope is negative, the gradient function is below the axis. Whenever the slope is positive, the gradient function is above the axis. And at the points where the slope is exactly 0, the gradient function crosses the axis. Here are the official definitions then for increasing and decreasing functions. Provided the gradient function f dash of x is at least 0, we would describe the function as increasing. And provided it's no greater than 0, so less than or equal to 0, we would say it's decreasing. And then the overlap between those two conditions are the stationary points. It's another reason why stationary points are so useful. If you want to know when a function is increasing or decreasing, one of the first things you do is you identify the stationary points, and then you know at which moments it will change between increasing and decreasing. And this is the extra bit I was talking about. We can describe a function as being strictly increasing, perhaps, if the gradient is positive as opposed to simply non-negative. Generally speaking, when we use the phrases increasing or decreasing, we include the or equal to in our inequalities. Next, we're going to try to identify some common misconceptions. We'll see how many of these mistakes you can make and have alerted to your conscious mind, so you're on the lookout for them as you work through questions. We're going to have a few true or false statements. When y is positive, so is dy by dx. If dy by dx is less than 0, then y is less than 0 also. If dy by dx is 0, then y is at a local minimum. If y is at a local minimum, then dy by dx is 0. A polynomial with 3 roots has 3 stationary points. And finally, if y is decreasing, then dy by dx is less than or equal to 0. Have a think about these. See if you can explain, for the ones you believe are true, can you explain why they're true? And for the ones you believe are false, can you give or describe a counterexample? That doesn't have to be a complete function that you've given the equation of, but it might just be a quick sketch. Okay, let's start with the first one. This is saying that if the function is positive, in other words, you're at a point above the x-axis, then the gradient is also positive. Now, in the diagram we've got on the screen, certainly for values of x that are above 3, that seems to be the case. And it's also true for between 1 and 2, it looks like. But in fact, there are lots of other places where it's not the case. So when x is minus a half, for instance, or when x is equal to 2.5, y is positive, but dy by dx is negative. If dy by dx is less than 0, then y is less than 0 also. This one is also false for similar reasons. Essentially, what it's saying is if you've got a negative gradient, then you must be below the axis. But that's not quite true. That's a bit like saying if you're moving downwards, you must be below sea level. It's not necessarily going to be the case. If you move downwards for long enough, then eventually you're going to get below sea level. If you're spending more than you're earning, eventually you'll be in debt. But that doesn't necessarily mean you are automatically. So we have to remember the gradient of a function in some ways is independent of the function itself. Not entirely, obviously, because in the long run, the gradient function determines how the original function changes. So for a positive gradient, in the long run, a positive gradient will drive the function to be positive. But if you shift the graph up or down, that doesn't change its gradient function. The gradient for a particular value of x will be the same whether the curve has been translated up by 50 units or down by 2,000 units. It's not going to change the gradient function itself. If dy by dx is 0, then y is at a local minimum. This is false. We've got a classic counterexample here. At roughly x equals 2, we see dy by dx is 0. We've got a horizontal tangent at that stationary point, and yet that particular stationary point is not a local minimum, it's a local maximum. However, the converse of this statement is true. So if you're at a local minimum, then because that's an example of a stationary point, it's a point where the gradient is 0. Remember that just because you've got a particular statement which is true does not necessarily mean the converse will also be true. It's very often the case that the converse is not true, even though the original statement is. The next statement, a polynomial with 3 roots has 3 stationary points. A little bit deceptive, because our diagram certainly seems to fit that description. 3 stationary points, min, max, min, and 3 roots, 0, 1, and 3. However, in general, it is not the case. Try sketching for yourself a cubic, and that will give you a more typical example of a polynomial with 3 roots, maybe y equals x times x add 3 times x add 5. It crosses at 0, -3 and -5, and it will have stationary points between -5 and -3, and another one between -3 and 0, but that's only 2 stationary points. You could construct a polynomial with 3 roots that had more stationary points than that. You just need to add a few extra wiggles that didn't go across the x-axis. So this statement is not true, but we can make a statement about polynomials with a certain number of roots. We'll get to that in just a moment. But first, if y is decreasing, then dy by dx is less than or equal to 0. This one is true by definition. This is essentially what we mean by y is decreasing. We mean the gradient is less than or equal to 0. It's either 0 gradient or it's negative gradient. That's what a decreasing function looks like. So, bit of extra detail. If you take a close look at a local minimum, you will find that it's not just that the gradient is 0, but the gradient is transitioning from negative to positive. As you read from left to right, at a minimum, the gradient goes from negative to 0 to positive. The opposite happens at a maximum, where it goes from positive to 0 to negative. And then the third edge case, the point of inflection, the gradient might be positive and then 0 and then positive once more, or perhaps the opposite, negative then 0 then negative once more. So the way we can identify the difference between them is something to do with how the gradient itself is changing. And we'll talk a little bit more about that when we get to the second derivative, because the second derivative tells us how the gradient is changing in the same way that the first derivative tells us how the original function y is changing. The last thing I promised, a polynomial with n roots has at least n-1 stationary points. So this is a statement that is true. Look at our example just above. We've got 5 roots and 4 stationary points, and it wouldn't be possible for us to have any fewer than 4 for a polynomial because, well, for a start, if a polynomial crosses in 2 places, then at some point it has to turn in between. It crosses the x-axis on the way up, it's going to have to turn in order to cross it again on the way down, which means there'll be a maximum between those 2 roots. And similarly, if it crosses the x-axis going down, it's going to have to turn through a minimum to get back up again. This is not necessarily true for all functions because you can have all sorts of weird things going on, discontinuities, asymptotes and so on, but for a polynomial we can be confident of this. Some functions are increasing throughout their domain. For instance, y equals 2 to the power x is always going up no matter where you look, but other functions will be increasing in some sections and decreasing in others. So a typical question would be find the values of x for which this function is increasing. And the first thing we're going to do is rewrite it in index form. If you've got reciprocals or radicals like square roots, the first thing you want to do is turn everything into powers of x so that you can differentiate more easily. X differentiates to give 1, but 16x to the minus 1 differentiates to give minus 16x to the minus 2. Bring the power down in front, reduce the power by 1. The reason we want the derivative is that a function's increasing or decreasing will depend upon whether the gradient function is positive or negative. So what we're interested in here is finding out when f dash of x is greater than or equal to 0. Remember, it's a broader definition for increasing, so in general we're thinking positive gradient, but the edge case needs to include 0 gradient. So we're trying to solve this equation. You'll notice I've gone right back to reciprocal form instead of index form because now I'm trying to solve an equation. The first thing I'm going to do here is multiply both sides by x squared. That gives x squared minus 16 is greater than or equal to 0. And this is a quadratic inequality. We can solve it by first factorizing and then identifying critical values. But first of all, there is something that's just happened dealing with an inequality that we need to be a little bit cautious of. In general, if you multiply both sides of an inequality by a negative number, then the sign changes, perhaps from greater than to less than, etc. If you multiply both sides by an unknown, like x or 7x cubed minus 3, then the sign might change or it might not. And in fact, more precisely, depending on the value of that unknown, the sign will change or it won't. Why was that not a problem for us? In this case, have a think. Why was that not an issue when we chose to multiply by x squared? I'll let you have a think about that to set your mind at rest. We're okay. This does work in this particular case, but have a think about why. Next thing we're going to do is find the critical values. We do that by thinking about when the quadratic is equal to 0, and we get x equals plus or minus 4. We use a sketch then to solve the inequality. So look back at the quadratic inequality and you'll see it's a positive quadratic and it crosses at 4 and at minus 4. So we'll do a quick sketch. It'll look something like this, and you can easily identify from your quick sketch the values of x for which that quadratic is greater than or equal to 0. It's going to happen either when x is less than or equal to minus 4 or greater than or equal to 4. And you could include the set notation version of this as well. It's a good idea to get into the habit of writing set notation. This is the set of all values of x such that, that's what the colon means, x such that x is less than or equal to minus 4. And then the other set is the values of x such that x is greater than or equal to 4. And we've used the union symbol in between to show that the entire set of all possible solutions is the union of those two sets. Now there's a few questions you can have a go at from exercise 12G. I've selected just a handful from questions 1 and 2, and then questions 3 and 4 are worth trying as well. Just finally, this is the graph of the original function f of x. In case you're curious, you can try that out on GeoGebra or use the same when you're working through questions from the book. I highly recommend it, help you to get a sense of what's happening. You'll notice here the graph does some crazy things in between minus 4 and 4. It's got an asymptote, but reassuringly we can see that the function is increasing precisely when we said it was. It's increasing from however far left you want to go up until the point where x is minus 4. From that moment on, it's decreasing. The gradient becomes negative and it goes down, down, steeper and steeper. Comes back from positive infinity, but it's still got a negative gradient right up until the point where x is 4. That's another stationary point, 0 gradient. And from that moment on, it continues with a positive gradient henceforth. If you're curious about what it's doing in the long run, think about what happens to x plus 16 over x when x gets really, really big. Right, sketching the curve. If we're looking at a function y equals f of x, then a useful thing to be able to do with that is to sketch the gradient function that goes along with it. And there's a few important things we want to get to grips with for that. Firstly, you want to be able to look at the graph and visualize what's happening as you move along it. So you want to imagine tracing it out from left to right as if you're riding the roller coaster, if you like, and you can visualize what's happening by thinking about the steepness of your tangent line. So what I've got here is a tangent line tracing out the function, and the gradient function is shown in blue when it appears. So you can see the height of the gradient function will represent the steepness, positive or negative gradient of that tangent line. Remember that because the gradient function is the slope of the original function, it could be positive even when the original function is negative, and vice versa. So I've got a couple of analogies for this. Let's say y represents my bank balance on day x. So as we move from left to right, we're basically moving through time and the amount of money is changing. dy by dx will be the rate at which the bank balance changes. So if dy by dx is 20, it means I'm getting £20 more in my bank every day. If dy by dx is minus 100, then my bank balance is going down by about £100 a day. Now, if I'm in debt, but I'm earning more than I spend, that means that the value in my bank is currently negative, but the rate at which that number changes is positive. So y is less than 0, but dy by dx is greater than 0. If, on the other hand, I'm in credit, but spending more than I earn, then this is the opposite situation. Y is greater than 0. The amount of money is positive, but dy by dx is less than 0 because I'm losing money as the days go by. You might want to ask yourself, which of these in the long run is the better position to be in? Would you rather be in debt, but living within your means and gradually paying off your debt, or would you rather have savings, but be gradually eating into them? Here's another example that you might find more helpful. This is the more physical or mechanics example. If y represents your height at time x, dy by dx tells you the rate at which the height changes over time. So if you're below sea level, I'm using sea level as my default 0, but moving upwards, then perhaps you're a submarine captain that's coming up to periscope depth. Y is less than 0, but dy by dx is greater than 0. On the other hand, if you're already above sea level but you're moving downwards, so now you're a blimp captain who's losing altitude, y is greater than 0, but dy by dx is less than 0. Now, this is the thing that's really going to make you think. If you're above sea level, so y is greater than 0, and you're moving upwards, so dy by dx is also greater than 0, but you are subjected to a downwards force, and hence a downwards acceleration, so that d2y by dx squared is less than 0, what will eventually happen to dy by dx and to y? So this is the situation we have at the moment. I have a ball, and if I throw it up, it's going to be initially moving upwards and also above the ground, but it will be subjected to the downwards force of its own weight. Gravity is going to be pulling it down. And since gravity continues to pull it down, ultimately think about what the effect will be initially on its upwards velocity, dy by dx, and then eventually on its vertical displacement, its actual height above the ground. Have a think about that one. Now we're going to try some gradient function clues. I want you to have a look at the following statements that I'm going to put down. Think about what's the minimum number of these clues you would have to be given in order to know for sure that the point being described is a minimum point. The first clue is the y-coordinate is negative. The next clue, the curve has a repeated root at this point. The next clue, the second derivative is positive. The first derivative is 0. And finally, the curve is a quadratic. So there are 5 clues. Which of these would you need to be told in order to know for sure that the point that I'm describing is a local minimum point on the curve? Have a pause, think about it, and then come back. Okay, so first of all, the y-coordinate is negative. This is a classic red herring. This particular point is completely irrelevant. The height of a point gives you no information whatsoever about whether or not it's a minimum. The curve might be, in general, below the axis, and even its maximum point might be negative. We don't know for sure what's going on with the curve, but knowing the y-coordinate doesn't tell you a whole lot about the gradient of the function. Next, the curve has a repeated root at this point. Well, that sounds positive because although being a root is not necessarily relevant, a repeated root certainly makes it sound like it's going to be a stationary point. However, although this is enough to prove that we're looking at a stationary point, it's not enough to prove that we're looking at a minimum. I'm using the phrase sufficient but not necessary here. It's wording that you'll come across more if you do more mathematical proof as you move through your studies. This is sufficient to prove a stationary point, meaning if this is the case, we know we're dealing with a stationary point. But it's not necessary because you could have a stationary point without this being the case. An example would be, I suppose, if you've got a truck driving license, that is sufficient for you to be able to hire a car. However, it's not necessary for you to be able to hire a car. It's kind of, you could argue that it's strictly more than you need perhaps, or maybe it's just one possible alternative. If you've got your CBT, then that's sufficient for you to ride a motorbike. But if you don't have your CBT and yet you do have a driving license, that would also be sufficient for you to ride a motorbike. So perhaps alternative ways to satisfy conditions. In this particular case, that condition is sufficient for a stationary point, but it's not necessary for a stationary point. And it's not enough to prove that that stationary point is a minimum. You can have a repeated root, which is a point of inflection or a maximum point as well. Similarly, the curve is a quadratic, doesn't tell you that the point you're dealing with is a minimum. Even if you know that it's the vertex of the quadratic, it still could be a maximum or a minimum, depending on whether the quadratic is a positive or negative quadratic. The two key things in here that are going to give us information about whether the point is a minimum are these two. And in fact, either of them on their own is not enough. The second derivative being positive and the first derivative being 0 are both necessary for us to know for sure that we're dealing with a minimum point. So have a look at this minimum, and hopefully you'll be able to get a feel for what's going on. The gradient is 0. We're happy with that. That means at the minimum point, the slope of the function is 0. But what about that second derivative? Well, remember, dy by dx tells us the rate at which the original function y changes. d2y by dx2 tells us the rate at which the gradient changes. So when I say that the second derivative is positive, it means the gradient, dy by dx, is increasing. Now, if you follow this curve along from left to right, you'll see that that's exactly what's happening. The gradient is increasing. In fact, not just at the very bottom, but all the way through this section of the curve that you can see on the screen, the gradient is increasing. It starts out relatively steeply negative and gradually becomes less and less negative until it becomes 0 at the minimum, and it continues to increase, becoming small positive and then larger positive as it goes along. So if the gradient is simultaneously 0 and increasing, then we're at a minimum point. And you can see that because the gradient is going to be negative just before the minimum point and positive just afterwards. In general, we can generalize this whole idea to something called the second derivative test. If we're at a stationary point, in other words, dy by dx is 0, and the second derivative is positive, then we have a local minimum. Now, the second derivative will give you, in general, an expression, an algebraic expression, just like the first derivative. So this is a case of substituting in the value of x at that stationary point. And if you can say, at this point, the second derivative is positive, if you also know that it's a stationary point, then you now know the type of stationary point. We call it the nature of the stationary point. So we can determine the nature of a stationary point by looking at the second derivative at that stationary point. The next one is what happens when the second derivative is negative. We have a local maximum. And now it's worth emphasizing at this point, people often get confused because we have the impression that greater than 0 and minimum seem like they're the wrong way round. We feel like we ought to have less than 0 going with minimum and more than 0 going with maximum. But in fact, it's to do with the fact that at a minimum point, it might be low, but it's as low as you're going to get for the time being because things are on the up. And the second derivative is describing the long-term trend. So if you're at a minimum, it's like you've hit rock bottom. You're not going to get any worse. If you're literally at your minimum, that means things are looking up. Things are about to get better. And that's what the second derivative tells you. dy by dx is 0 means that at the moment, you're not going up or going down. But the second derivative is positive, which means soon you will be going up. And the opposite happens with the maximum point. Think of it as, over the hill, they say. If they say things can't get any better than this, we've peaked, we've reached our maximum, that means that at this moment, things are pretty good, but shortly afterwards, things are going to start going downhill. So the second derivative tells us that the gradient is decreasing. Right now, the gradient's 0, so you're on the level temporarily, but shortly afterwards, the gradient's going to be negative. It was positive before, got to 0, now you've peaked, you can't get any better than this, you've run out of steam, the gradient is on the way down, so you're at a maximum point. The third option is the point of inflection. And this is a bit of a sneaky one, because, of course, if you take the second derivative test and you find a positive or a negative value for the second derivative, you know you're dealing with either a minimum or a maximum. But if you get 0, well, you've got a bit more work to do, basically. There'll be more that we do with a 0 second derivative. We'll investigate it further. But for now, it's sufficient to say that you would have to look either side of the point you're interested in to get a clearer sense of what the function is doing. You could look at the y coordinate on each side. Often it will be easier to substitute values into the second derivative or the first derivative. If you sub them into the first derivative, you'll get a readout for the actual gradient shortly before and shortly after. If you sub it into the second derivative, that will at least tell you whether or not the curvature is changing. But we'll talk more about that in second year differentiation. For now, if you're still curious, I recommend you try sketching the graphs y equals x cubed, y equals minus x cubed, try the positive and negative y equals x to the 4 graph, maybe draw them out in GeoGebra and try differentiating them a couple of times to investigate the stationary point that we find at the origin. And you'll get a sense of why a second derivative of 0 can hide a multitude of different possibilities. The last thing we're going to look at is practicing the use of the first and second derivatives when dealing with some functions. I've got some relatively nice functions here, so we can focus on what the first and second derivatives tell us instead of getting bogged down in the detail of how to differentiate the various things. I'd like to have a go at differentiating each of these 4 things, and then once you've differentiated them once, differentiate them again. You'll get an expression for both the first and second derivatives. You can use the first derivative to find stationary points. Remember, stationary points occur when the first derivative is 0. And then you can use the second derivative test on your f double dash of x to identify the nature of those points. So check to see if you get a positive second derivative, which would correspond to a minimum because the gradient's increasing, or a negative second derivative, which will correspond to a maximum because the gradient will be decreasing. Pause, have a go at this, see if you can sketch the curves and mark on the coordinates of the stationary points, see if they fit with your intuition about the quadratics or cubics in question, and then come back and see if my answers agree with yours. All right, here's my answers for these 4 questions. The quadratic reduces to something linear when we differentiate it once, and then all the way down to just a constant when we differentiate it a second time. In fact, if you think about it, every positive quadratic will always give you a positive second derivative, and vice versa. Every negative quadratic would always give you a negative second derivative. And it's not just that it's positive or negative for certain values of x, but for question 1, f double dash of x is always 2, positive. That means that no matter where a stationary point might be, it's going to have to be a minimum because the gradient throughout the entire function is always increasing. Well, it's a positive quadratic. That should be what we're expecting. The gradient's negative at the beginning, positive at the end, and it smoothly transitions between the two with no weird wiggles in between. So a second derivative that doesn't depend on x is kind of what we should expect here. The gradient is always increasing throughout for a quadratic. For a cubic, however, that's not quite the case. We can solve f dashed of x equals 0 for question 2, and we can find the coordinates of the stationary points. And this is what the graph will end up looking like. Your stationary points are at plus and minus a half for x. When you sub those numbers into f of x, you can find the y coordinates that go along with them. But you'll notice for this one, the second derivative is minus 24x. So now it does depend on the value of x. If you put in any positive value, like a half, then you'll get a negative second derivative, which means that not only at the maximum point, but also at any point with a positive x value, the curve has a decreasing gradient. Negative second derivative, decreasing gradient. And for any negative value of x, the curve has an increasing gradient, including the point where the curve is increasing, the curve's gradient is increasing, but also the curve's gradient is 0 at that stationary point minus a half 0. So any stationary points that occur for negative values of x will be minimums because the second derivative is positive, and any stationary points that occur for positive values of x will be maximums because the second derivative is negative. Here's the next one. This one's got some nice symmetry, and that's because it's an odd function. That means that all the powers of x that appear are odd powers, x cubed, x to the 1. Polynomials are not the only functions that can be categorized as odd or even, but an odd function is defined as a function that you could rotate 180 degrees about the origin and it would be exactly the same. So it has rotational symmetry. Y equals sine x is one example of a non-polynomial function that has the same property. Another way of thinking of it would be you can reflect it in the x-axis or the y-axis, and what you'll get will look the same regardless of which axis you've reflected it in. So you could describe that as f of minus x equals minus f of x, if you like. In this case, it gives us some nice symmetrical results. The stationary points occur at plus and minus 2, and their y coordinates are minus and plus 16. When we look at the second derivative for this, we'll see that we get a similar sort of pattern to question 2, but because this one is a positive cubic, we have a decreasing gradient when x is negative and an increasing gradient when x is positive. And that's why the first stationary point we come across is a maximum because the gradient's decreasing, and the second stationary point we come across is a minimum because the gradient is increasing. Now for the final one, when we differentiate the quartic, we get a cubic. When we differentiate the cubic, we get a quadratic, and we would need to solve the cubic from f dashed of x equals 0 to find the stationary points. Luckily, that's not too horrible because x is a factor. In fact, it's a repeated factor. We should be able to find 0, 0, and minus 1 for those. And then f double dashed of x will give us information about the nature of those, hopefully. Turns out this one's a weird one. The fact that there's a repeated root when you do f dash of x equals 0 is a bit of a clue. So minus 1, 4 is a minimum. 0, 5 turns out to be a point of inflection. The way you would demonstrate this is by testing values nearby. So if you look just to the left of x equals 0, so try something like x equals minus 0.1, and then look just to the right, like x equals 0.1, you might be able to see that the curve is increasing before and also afterwards. If it was increasing before and decreasing afterwards, we'd be at a maximum. If it was decreasing before but increasing afterwards, it will be a minimum. But if it's increasing before and after, or alternatively, if it's decreasing before and after, then we know we're looking at a point of inflection. Now there's a couple of questions from exercise 12i that you can have a go at, questions 3 and 4.